Hello, good morning, everyone. Can you hear me?
Yes.
Okay, good. So, hope you are, let's say, comfortable and safe, since the weather is not, let's say, so favorable today. Sorry, I hear noise in background. Okay, good. So, let's start the lesson. Okay. So first, do you have any question about what we have seen yesterday? Okay, so today I would like to conclude the presentation of the signal management. So let's share my screen. Can you see my screen?
Yes.
Okay, great. Thank you. So, just a second, I want to check. Okay, so yesterday we have seen interface and a possible implementation of the library. Let's jump back to these parts. So basically, we have seen a list of variables that, according to the implementation I presented yesterday, can be used to store the information we need for our signal management. So in particular, I commented the fact that we need some memory for the active signals and for the order of signals. A possible implementation could be to use a couple of arrays in which we will store Boolean variables to detect which signals are active or not, and another array to store the list of codes of the active signals according to different order and strategies that we would like to use to present our to represent the current state of active signals. We went through this code in which I commented mainly the different phases. So the fact that we need to start the configuration of signals by resetting all the variables we have that we used to count how many alarms, anomalies, warnings, and information we have in our system, and in the configuration phase we used the this case statement to count the different type of signals that we have. So this is the configuration phase. Then in the generation phase, we need first in the start generation, again, sorry, the slides is moving without control. We need first to reset the information we need to manage the reset and the output. So we reset also the state of the reset to detect the fact that it was pressed for the first time. The same is for the auxiliary reset. And then in the next section, we start the generation of the signals. And so we verify if we are considering an alarm, anomaly, and so on, in order to set proper index and conditions that can be used to manage the signal properly in the rest of the of this part. Then in the second section, we check if the activation signal is true and the signal was not true before. So in this case, this is the first time we see the activation signal for this specific code. And then we set this signal to true into the memory of active signals. We increase the index for that type of signal, and we store the code of this signal into the list of active signals into a proper position. Then we check in the second if condition if the conditions for the specific signal to be reset are satisfied in order to enable the reset. So we have to check that this is a resetable thing. So an alarm or an anomaly, the fact that it's active, the fact that activation signal is not present anymore, and the fact that this is the signal code that we have at the actual top list in the list of active signal, in the top of the list of active signals. So this, of course, doesn't take into account other, let's say, conditions that we can use to reset signals, so like auto reset and so on. So in case you need to, or you want to implement all of this, you have also to put this into account, to take this into account in this statement in order to eventually skip the fact that you need to activate the reset enable in case you will perform some auto reset functionality, or in case there's no activation of the alarm because of the of some condition of the reset policy. In the the second part of the generation, basically check if we can reset the active signal on top of our active signal list. So we check the state of the reset, the fact that this is a resetable signal, the fact that it is active, and that the activation signal is not active anymore, and that this is the signal on top of our active signal list. In this case, we reset the signal to false, and we basically remove this signal from the list of active signals, and we change the index accordingly, and we remove the reset signal. So we set back the reset signal to false in order to use this reset only for the active signal. In case you want to use a cumulative reset, of course, this we commented that this line can be removed. So we will preserve the reset active for the wall for all the signals, basically. Another extension of this code could be in case you want also to manage the auxiliary reset that is not considered here. So we commented about the how we can use the auxiliary reset, and so if you need to activate it, you have to add this into this management in a proper way. Then the last part is to again restore the right number of active signals after eventually resetting something. So we reset the number of active alarms, anomalies, warning, and information according to what was done before. And at the end, we save the output provided by the current signal. So this signal output is the output designed for the current signal, while this is signal outputs, so the plural, is the memory where we will store, we will sum in a logic sense due to this, or operator all the outputs into a single memory. So this is the overall output. Then, of course, this is what the machine has to take into account to react to what are the outputs required by all the signals. Finally, we have the run phase, in which we commented yesterday. Basically, what we have to do, depending on how the user interface is made, we have to exploit the information we generated before in order to update the user interface accordingly. Okay, so after this, to make our system, our signal management running, we said we need to add some operation mode to our machine. So if the operation type is the operation type of our overall machine, we need to consider that we need to add configuration generation, start configuration, start generation to the list of operation types. So this is what we will have at the machine level. And then we will also, for example, use signals that we will to configure, that we need to configure into the calls of our signal management function block in order to monitor what is happening in the machine. So then we need the reset signals. So these are the reset button and the auxiliary reset button. We need the output signals, so the ones that we will use to as output of the function block. And then out of this, we will take out also some information about the fact that the reset can be enabled, so to inform the user that the light can be activated. The same, these are actually the reset functionality activation and the three main stops. So the emergency stop, immediate stop, and on-phase stop. So these are the three signals that we said we need to feed back to our state machines in general, if we have more than one, to let's say to take into account what is commanded by the signal control in case there's some action to be performed automatically. Of course, we will have also the list of error codes, as was also, for example, for the PLC open function blocks, and some coding of the conditions that we would like to take into account to activate this emergency immediate and on-phase stop. And of course, this is the memory that we will use, reset hold and key reset hold, to store the old value of the reset and key reset function or auxiliary reset value. This enables to verify when the button is pressed for the first time, because we can, by comparing the old value with the new one, detect when there's the change from the false to the true value. So we can really detect once when the button is pressed just once, not, let's say, to consider that we have to perform more resets if the operator stay on the button. So if the button is permanently pushed or pushed for let's say more time than needed. Then of course we need an instance of our signal management function block, that is this one. So this is the signal management library that we define, and this signal management is the instance of the library that we used to monitor our machine. Then these are the signals that we used to validate that the reset can be actually engaged by the user, because there can be conditions in which the reset is not allowed for some reason. These are the reset buttons. As I said, we compare the value we have stored in memory in order to check the fact that the button is pressed for the first time, and not, let's say, that the user is not continuously pressing the button. The same is for the auxiliary reset. Then we have the how we control the switch between the different operation type inside the machine to drive the signal management. So basically, during the init phase, the signal management has, let's say, nothing to do according to our implementation. Maybe you can also do something if you need, but actually we have a specific initialization for our signal management, like the start configuration phase. So you see here, when we are in the init phase for the machine, we call explicitly the signal management with the operation type set to these values. Okay, init may be not needed, so we can eventually skip this first line. For sure, we need the second to reset the information about the configuration of signals. So during the initialization of the machine, we clear whatever we have in our signal management function block to then start storing information about what we actually have. And then we set the operation type to configuration. So what does it mean, this? We perform a single call of the signal management function block with the operation type init if we need. Otherwise, we can skip this. We call a single call of the signal management function block with the operation type start configuration to reset the information. Then we set the operation type to configuration. But note, we are not calling the function block. So we are just setting the operation type input to the configuration value. It means from now on, if we don't change this input, the signal management function block will work in the configuration phase every time we call it. Okay, you have to understand this mechanism. So in this way, we can call every time the signal management to perform a different thing. So start the configuration, so clean the information about the configuration of our signals, and then start configuring the signal. But this is just the start. The configuration operation will last much longer, because we need to call for each configured signal. We will call the signal management function block with this operation type configuration in order to store the information about all the signals. And this is done in the operation in the init phase. So if you close, basically, suppose that you in your first implementation of the signal management, you will close your code here. So what you're doing right now is just when you run the machine during the init phase, you will go through the whole list of signal configurations, and at the end of this, in your signal management function block, you will have all the information about how many signals you have of each type, because you read them during the initialization. Then, of course, the operation type of the whole machine will change to run. It means next time, if you don't make any other adjustment, let's say, to the operation type, when you call the signal management, it will always repeat the configuration. That means it will count the signal more and more. So, of course, it's not what we would like to have. So what we like to have is the first time in the init phase, we will configure our signals in order to store the information. Note that since until we stay in the operation type init, so the machine is in the initialization, basically the signal management every time clean the memory and read again the configuration. So basically, even if we stay in the operation in the initialization phase longer than just one cycle, is not important. It means just that every time the memory is updated, it may be, let's say, a waste of time, but it's just for initialization. Then, so this is what is after the else statement. It means the machine is not in the initialization anymore. We are then in the running phase for the machine. So what we will do after the initialization, so we already stored in the configuration phase the information about our signals into the signal management. We will call once, just once, note the syntax here. We call during the running phase at every time during the running phase the signal management with the operations type start generation. So it means the first time we will just reset the information about what we need to generate the signals. So basically, we reset, we clean whatever we need, and so on and so on. Then we set the operation type to generation. Note the difference between these two. So basically, during the initialization of the machine, the signal management is cleaning the configuration memory and read the configuration. While in the running phase, so during the nominal behavior of the machine, the signal management just clean the information about the actual state of all the reset information and stuff like this. So what we need for the generation of signals, and then execute the generation because the operation type is changed to generation. Of course, if you have questions, please stop me, raise your hand, open the microphone, whatever. Okay. Good. So then what we have to do after these steps is just to have the list of hundreds, thousands, whatever are the number of signals you have in your machine, or the number of configurations of this function block that you have in your machine for each single signal or configuration. It means first you select which is the proper operation type for the machine, eventually first resetting memories during the initialization for the configuration, during the nominal behavior for the generation, and then you change to or configuration or generation. So what does it mean? If you are in the init phase, you will first clean the configuration memory, and then you will start configuration. Then when you call again the signal management function block, the operation type is configuration if the machine is in the init phase. So it means from this configuration, the signal management function block will read the type of the signal, eventually other configurations that are needed, and this will be stored in the memory, the configuration memory. Then this is repeated for all the signals. Okay, so this is just once, but suppose here you have 2, 3, 100, 1000 call to the signal management function block with different configurations, so different type, different code, different output, different signals, different authorized conditions, and so on and so on. So every time you will have the operation type fixed to configuration, so you will store into your memory inside the signal management the number basically of signals according to their type that you have, and any other information that you need to manage them during the generation. Then, when the machines switch to the nominal condition, so to the running phase, first you will, let's say, reset the information to manage the generation. Second, the operation type will be set to generation, and you will again call all the configurations of your function block. So when you read this configuration first, you will check if the activation signal, this activation signal is true. Then this is classified as an alarm, as a certain signal code, generates some output. So you will decide what to do with this signal according to the actual condition, the configuration, and so you will generate the output or the change in the signal management unit given the actual condition of signals in this call. And the same is for all the others. Okay, so this is not okay. In this case, it means we just have one signal if you take the code as it is, but you have to think that after this, you may have hundreds of different calls to the same signal management function block with different signals and different configuration. Then the last point is to actually call the operation type run of your signal management. It means only when the machine is in the running phase and just once, you will call the signal management with the operation type equal to run. That means we would like to update our user interface at the end of the call of all the signal management. So once the memory of signals and active signals have been updated correctly about the state of all the signals and so on during the generation phase, so we have what we need to correctly update the user interface. So the user interface is updated just once at the end of this list of calls. Okay, then of course we have to generate the signals that we need to feedback to our finished state machines. Then of course we can also, let's say, activate lamps, bells, whatever we have in our machine according to the outputs that we may consider. But for sure, we have to generate the feedback to the nominal controller, so the finished state machines. So these three signals are the ones that our finished state machines have to take into account to verify if actually there's some emergency stop, immediate stop, or on-phase stop that are commanded by the signal management. And this is the way how we can, by using the same bit field mechanism, bit mask and bit field mechanism that we have seen, for example, also for generic devices, we can take out of the whole list of active outputs if an emergency stop, an immediate stop, or an on-phase stop have been requested. And then on the base of this, of course, the emergency stop will be more relevant than the immediate stop, and the immediate stop will be more relevant than the on-phase stop. So according to this, then our finished state machines will react to the request of the signal management.
Sorry, Professor. Can I make a question?
Please.
I don't know if I got it right or not, but did you point out that there is a difference between accessing the operation type in the signal management in the if then else? Accessing the operation type with a bracket or with a point? Because I didn't get that.
Yeah. Okay. The difference is that okay, take the first line here, signal management, then bracket operation type init. Okay, this is actually a call to the signal management function block with the operation type input set to init. Is it clear?
Yeah.
Okay. Then if you take the third line here, this signal management dot operation type equal set, not equal, set as configuration is not a call to the signal management function block. You just set the input of the signal management to this value. The call is actually down here. Is it clear?
Yes, but yeah, I think that it's like the same instance. So if I
Yes.
call it or if I change the value directly, isn't it going to behave as like the same?
I'll try to clarify. So basically, in the first line, you call the instance is always the same. Yes, of course. We will have only one instance of the signal management function block, otherwise it doesn't work. Okay, it may work if you use global variables, but okay, let's take it simple. So in the first call of the signal management, we don't care about the other inputs. The same is for the second, because if you remember, when we have this operation type, for example, start configuration, we completely neglect the init phase. This is the reason why we can avoid the first line. In the implementation I presented before, there was no use of this value of the operation type, so you can remove it. In this second line, during the start configuration, the only thing that we did in the implementation is to set the counters, basically, of the signals to 0. So it means you don't need any information about other inputs of the function block. So the list of inputs of the function block are this one plus the operation type. If you go back, I want to move back here. These are our inputs. So this is the list of inputs of our signal management function block. In the second call we had in the previous slide, we are just considering the first input. We are neglecting completely the other because what the operation type start configuration does is to just reset internal counters. Okay, so we don't care about other inputs. Okay.
Yes.
So while in the third line, when we set the operation type to configuration, we just set this input, but we don't call the function block. The function block is called later when we provide also the other inputs.
Okay.
And this is because for the operation type configuration, as well as for generation, we need to consider also the other inputs to do what we need to do. Okay. So let's say after the third line, we set the operation type to configuration, and the call is actually this ones because there are brackets including the list of inputs that we need. Eventually, you can also write this in a different way. You can first set all the inputs and then call the function block, as we did, for example, for the generic device or the generic axis. Is the same. Of course, you have every time you have to configure or generate another signal, repeat the same. So for another signal, you have to set first all the inputs properly and then call the function block every time.
I got
it. Okay. So when you have brackets, it means is a call to the function block. When you have dot and the input name is just, you set just the input value. So it's storing the information.
Okay, so I didn't understand like that we are imposing some input, and after that we got to call the function in the signal management, signal type, signal code, etc. Okay, thank you.
So after say so basically in this if statement, you can recognize the first set of instructions that are used in the init phase and the second used in the running phase, basically. So it means first you need to initialize the signal management or in the initialization to start the configuration and then make the configuration by calling all the whole list of signal configuration that you have here. In the running phase, you will first reset the generation and then set the generation to be called for all the list of signals down here.
Okay, thank you.
Okay.
Prof,
please.
Can I ask a question? I didn't understand why we have two if with the operation time. Isn't it better to put the last line of signal management operation type dot equal run in the second part of the first if?
In the second part of the first if, you mean here? If we set this here, it will be called immediately before the call to this signal. If you put this line here, this is your question.
Okay. Yes.
This call will be made immediately, not after the update of the information done by these calls. This is the reason why we set this after, and we made this only in the running phase, because if we don't put inside this if statement, this will be done also during the initialization. That maybe could be something that you, for some reason, you can do. For example, in case you want to update also during the machine initialization the user interface with some information about the configuration of the signals. It can be. So take this as a potential implementation of the mechanism. Is to understand the mechanism. Then, of course, when you know what happened in the system, how the system works, then you can, if you want, for example, to execute the running operation of the signal management also during the initialization, you can just remove this if statement. The important point is that this run operation, according to the implementation before, is done after the call to this the whole list of signal that you have, because otherwise what you will update is not taking into account what are the configuration of each signals.
Okay, thank you very much, Prof.
There's an hand, Simone, please.
Yes, can you hear me?
Yeah.
I was wondering, the start generation, the signal management with the operation type start generation is done every clock of when we are in a run phase. Is done for every clock the first time. But and then we have several call of the signal management with the input generation for how many signal that we need to manage. But how we know that it's enough one call for that signal to be prepared, and the next call of the signal management with operation type equal to start generation will not cancel out the information that we take preview in the preview instance of real time.
In the start generation phase, we basically just clean what will be updated next. So, for example, if we go back to the implementation here, you see we just clean the outputs, clean the reset enable, reset the memories of the reset buttons that are actually also done out of in the previous implementation. So this, for example, is something that is done twice in this implementation. So you can remove one of the two. So this is just something that it will be regenerated according to the actual state of the signals. So basically, we are not canceling anything from the internal state of the signals. We are just cleaning what will be generated on the base of the state of the signals. So, for example, the fact that we can reset or not an alarm, the fact that given the actual set of active signals with EMSA output that are generated, the fact that the reset is active or not because the button has been pressed for the first time or not, and so on. So there's nothing that is cancelled. We are just preparing the signal management to do what is requested to do on the base of the state of the other signal. Is it clear?
Yeah, now it's clear. Thank you. And if I can ask another question, so all these signal program that for every signal management that we need to call, we need to create a call of that instance. So in the next slide, we can have a lot of calls in the middle.
Yes. For example, just back. Please go on. So I'm moving back to a slide where there's some. I miss where it is. Sorry. Here, for example, this is an example of 4 calls with 4 different configurations for 4 different signal types. So this is just a set of 4 calls that we will have in. Okay, sorry, I moved back. So these are 4 calls because we have 4 signals, and then we want to monitor this. But if you have 100 signal, you will have 100 calls, each one for each signal. We also commented the fact that there can be cases in which you may also call twice or even more than twice the function block for the same signal with different configurations, like in the case of corrections, like this. Okay, even if we commented the fact that it could be not, for some reason, the best solution, these are 2 calls of the signal management function block with the same activation signal, but different configurations. And you can extend this as much as you prefer. Okay, there's no limit in the flexibility of this mechanism. This is the reason why we use this mechanism. We want to be flexible. So every time you need to consider a specific configuration for a specific signal, just add a call of this type to the whole list, no matter how many you already have. This is the point.
Okay, got it. Thank you. And but since this is, I think, a way of time consuming, what is a comparison in the cyclic time that we need to set this program respect, I don't know, like the motion program?
Usually, this is okay. This question that is perfectly, let's say, in line with this topic, open other points. Of course, usually due to the fact that you have to make many calls to the signal management function block, of course, it may happen that depending on the power of your CPU or your PLC, it may require time to do all these calls. So maybe this function block is not something that is run at very high frequency. Then this could, okay, first you have to consider that in a complex machine, you really have thousands of potential faults. And then in any case, you have to check all of them, okay, if you want to use them, okay? So the first point is, if your machine is complex, no way. It is better to be more flexible than to save some, let's say, limited in some sense time, because in any case you have to check all of them by, I don't know, try to optimize the way how of course you can try to optimize the way how this mechanism, let's say, consumes CPUs in your system. But in any case, if you have thousands of signals, and this is common in a let's say machine like the ones are made today, the problem is there. There's no way to skip it completely. The other point is if your signal management is slow in a reaction, for example, suppose that you run this function block with, I don't know, 500 milliseconds timing. It means alpha second. Every alpha second you update the state of the signals in your machine, because otherwise your PCU, your CPU, your PLC is overloaded, and then you can, because you have so many signals, and then you are not able to manage this. This can cause serious safety issues if, for example, you have to stop your machine in case some protective device is open. Of course, to postpone the stop of the machine in the worst case by alpha second or even more, because there's no, let's say, theoretically restriction in how large can be the sampling time of this part of your machine. This is up to you, of course. That one can try to take it as short as possible, but sooner or later you have to take into account which is the power of your PLC and the complexity of the machine. So suppose that you have alpha second delay in reacting to the opening of a protected device. This could have very, let's say, serious consequences. So for that reason, we will not enter in this point because, let's say, there's no time, and let's say the story is also pretty simple to be considered in this case. There are parallel safety mechanisms that are mandatory in every machine that automatically trigger, let's say, the activation of, let's say, emergency stop, mainly in case there are serious emergency issues in the machine. So I didn't mention this, but if you consider a real machine, once a signal is considered something critical for safety conditions, like the opening of a protective device, this is also managed in parallel by a separated and devoted system that only takes into account the safety of the machine. So basically, this mechanism can be used to show to the user what is happening, update the state of the finished state machine in some way to let the machine know that something happened. But, for example, the stop of the machine will be driven explicitly by the hardware, because the hardware has specific safety inputs that are driven by a parallel mechanism to stop the machine immediately. Immediately means in a matter of microseconds, not something that the PLC in every case can't guarantee. Okay, this is there is a specific topic that is designing safety-oriented controllers. But say in modern machines, the safety is a separated system. The safety is not part of the PLC. The safety is managed by another. It's called safety PLC. Is another PLC, and actually inside this PLC you have at least two parallel different ways of implementing the mechanism for safety reasons, and they have to agree. Otherwise, it means you have some issue in the safety. And this also generates safety outputs that stop the machine, because it means you have some problem into the safety, and if you have problems in the safety, the machine can't run at all. So it's a parallel mechanism that just take into account what are the critical things into your machine, and the minimum set of things in this sense is, for example, protective devices. If there's some protection device or emergency button that is activated or deactivated in case of protective devices, The safety PLC, that is another mechanism, and actually this mechanism is really simple and straightforward. It's made by very simple circuitry that just trigger the right inputs into the machine to stop everything as soon as possible in a matter of microseconds. Is it clear?
Yes, thank you.
Okay, so good. That's it. If there's no other questions about this topic, okay, I would like to again stress the fact that what I presented is I would like to consider this more as a concept. Of course, you can use this as a trace for the implementation. Don't take this as for all the other parts of this course as something that must be like this. Okay, like maybe, but not. This is not the solution. This is let's say a guideline for a solution. So there can be many change sections, different implementations, as I already said. So please also for the other parts consider this during your development. Then finally, if there are no other questions, I would like to present you the final project. We are actually two different possibilities for the final project. I will start from the first one. This is the first assembly line. This is a real system that we have in our lab, not in the lab 5, where we have our laboratory sessions, but in another lab close by. So people that are interested in developing this project as last project can also use the real platform. I will show you in some video. You can also use a simulation platform if you want to develop this. I will show this later. Then there will be a second option for the last project that will only be based on simulation that I will show later. Okay, let's go through the first assembly line. This is the platform we have in our lab. It's made of 4 sections or stations: distribution, testing, processing, and assembly. You can see we have also a small robot in the last assembly station. So these are the 4 stations: so distribution, testing, processing, and assembly station. The distribution, as the name said, is used to distribute pieces to the rest of the machine. Then we have some testing that is used to perform some measurement on the pieces that are moved there. Then we have some processing in which some machining operations, some measuring operations are simulated. Let's say we have real tools, but the operation are just simulated to avoid, let's say, consuming the parts. And then the last, the assembly station, in which we have a robot executing the assembly of a product. This is the workflow in which we have, starting from the left side, the pieces, that is basically a cylindrical object with something inside that is used to build is something similar to a pneumatic piston. Of course, is a fake. It's not real, but it has all the components of a real, the body of a real pneumatic piston. So we started from the left side having the body of the piston in a warehouse. This is taken from the distribution station and moved to the testing station when there's some measurement like the height and the color that are verified on the body. And on the base of this, in particular on the height, the body can be say moved to the next phases or discarded if the height is not the right one. And then in the processing station, we check if the orientation of the body is correct, because the body can be also flipped upside down, sorry. And then we simulate some drilling operation. Then the piece is moved to the assembly station, and the robot then takes the body and put it into an assembly box, and then takes other components, the piston, the spring, and the cap, and mount all the components over the body. And at the end, take the final product and put it into a final warehouse. In case there's some trouble during the processing station, the body is just discarded by the robot. It's taken and thrown in a trash bin. These are the components of the final product, so cap, spring, piston, and body. The piston can be black and silver, depending on the size of the body. The size of the body can be detected by the color of the body. And the body are also taller or shorter, depending on the color. And we also have some pieces that are, let's say, out of expected measure in order to be discarded. Okay, this is the controller. Is a, let's say, pretty old PLC if you compare this to the PLC you used for the previous two projects. In fact, you can see that all the cabling is directly on the, let's say, connected on the PLC. There's no field bus. There's just a, let's say, a transmission system, so a field bus internally to connect these modules. So this is, let's say, a old style PLC, but is still something that you can find in a machine. We are also we have in plan to update this, but this is still what we have in the system. A very important thing in that project, this is true also for the other, is the fact that, of course, one main objective is to control the sequence in the right way. But as I will show you, let me say that theoretically all the elements in that station, in that assembly line, can be seen as a generic device. So the control is pretty simple of each device. Of course, to manage the whole sequence is not so simple. Even to manage the real hardware is even harder. If the people will try to run the system on the real hardware, will realize that it's not so simple to make it working, because you have to tune everything in order to be able to run properly. But I said the most important thing in this project, also the other variant of this project, is to show that you are able to manage signals. So the focus in this project is on signal management and on, let's say, the design of the sequence. So basically the use of generic devices and the design of finished state machines. But let me say that, okay, generic devices is basically something that you can take directly from the slides. The design of the finished state machine, okay, you have to consider all the steps, but they are not so complex. You have many. but it's not so complex. Of course, how to organize this in the best way is one of the main topic in the design of the finished state machines. I said finished state machines because this is a suggestion. You have 4 stations, so I suppose a good organization is probably to have one finished state machine for each station and a finished state machine managing how the different stations are connected one to the other. But I said the focus here is also on signal management. And to do this, in the real system, we cut the connection between the PLC and the hardware. So there's no direct interconnection as it is supposed to be in a machine like this. But we pass this connection, so the cables, through a switchboard that we can use to simulate any sort, not actually simulate, to really inject into the system any sort of fault we may have in the signals coming or going to the hardware. And I like a lot to play with this switchboard during the exam. So this is a message for the people developing these projects. You have to focus on how the system will react to faults, so signal management and so on. Because during the exam, what I will do is test how the system you will fault is injected into the system. Okay, so through this switchboard, I can force every signal to be true or false independently from what is happening on the controller or on the hardware. And of course, this makes the story interesting for the signal management. Okay, here we have some video. I hope you can see them. This video show the distribution station that you can see is pretty simple. The video is always the same, repeating over and over. There's this, okay, I will try to stop the video in the first part. Okay, sorry. Okay. So here you see the pistons. Here we have silver pistons in this warehouse that are moved out of the warehouse by, okay, the image is not updated. Okay, here you've seen, here we have a pneumatic cylinder moving this body out of the warehouse. And then there's an arm here. Again, this is actuated by a pneumatic motor that move up to over the body, and then thanks to a vacuum, take the body and move it to the next station. So you can see here the body, the arm move over the body. There's a vacuum here that is activated, and then this moves the body to the next station. Okay, sorry. I'd like to show. Okay, I don't know why it moves directly. Probably because it's too fast. In any case, okay. How here you can see the arm lifts the body and move it to the next. I'm trying to stop it in the right position. Okay, no way. I'm not able to stop it in the right position. Okay, here you can see the arm moving the body in the next station and deposit the body here. It will be shown in the next phase. So this is a scheme representing the distribution station. It's pretty simple. Here you have the warehouse for the body. Okay, you have some component like pressure regulator. Every actuation, apart from the robot and the rotary table, is pneumatic in this assembly station. Here you have the arm. Okay, you have all the interface, some electro valves that are used. You have other components like the vacuum sensors and whatever. Okay, I'm skipping this because I guess it's not interesting to focus on these hardware components. It's more interested to focus on the scheme of this distribution station using a similar representation to what we had, what we used when we presented the arithmetic junction unit. So the distribution station is composed by these devices. Okay, first let's talk about devices. We have a pneumatic cylinder that has single actuation and double feedback that is used to extract the bodies from the warehouse. We have a sensor that feels the presence of the warehouse, of the bodies inside the warehouse. So if the warehouse is empty, this sensor can be used to detect this condition. We have a vacuum that is a single actuation, single activation feedback device. We have also another device here that is actually we can invert the direction of the air in the vacuum to eject the object from the vacuum. And we have the arm that is a double actuation, double feedback device in the sense that we can use two signals to move the arm back and forth, and we have stroke in the two positions, in the two limit positions. So these are the signals associated to these sensors. So number one, the signal is called empty warehouse. So this is true when the warehouse is empty. We have the activation signal for the cylinder and the two feedback from the sensors providing the position, let's say in the contracted phase and to the extended phase of the cylinder. We have the two activation signals for the arm that moves the arm back and forth, and the two sensors in the two extreme positions. These are the signals for the vacuum. So the first is to activate the vacuum. The second gives you a feedback when the vacuum is active. And the number 5 is the expulsion. So to eject the object from the vacuum, to be sure that the object is actually detached from the vacuum. Okay, the objective of this distribution station is just to move bodies from the warehouse to the next station. And so in the warehouse, you may have multiple bodies, and you have just to separate one by one and move to the next station. So usually, not usually, to say the initial position is considered with the ejection cylinder extended. It means it is out of the warehouse. When you retract the ejection cylinder, you have an element that moves through the warehouse to get the body out of the warehouse. The rotary arm is in position warehouse, so is on that side, and the vacuum is off. So this is what is considered the initial position for these devices. So the distribution station at first to activate the arm to move it to the opposite side, that is called downstream station, before pressing the start button. This is because otherwise there's a collision between the object coming out from the warehouse and the vacuum. Then we can activate the ejection cylinder, retract the ejection cylinder to push the body out of the warehouse, and then move back the arm to the warehouse in order to activate the vacuum. And once we have the feedback from the vacuum, we can move back the ejection cylinder to release the body, and then move the arm back to the downstream station. Note that here the ejection cylinder is moved back after the arm has already, let's say, taken with the vacuum the body This is not mandatory, but is suggested because the risk is that when you move back, if you move back the ejection cylinder before the arm, when the arm goes down, because the motion is not controlled, this is let's say a generic device, you have no control on the motion of the arm. This is if you have an electric motor with a generic axis, so you can control the motion and then can solve the problem. But the problem is that the collision, let's say, between the arm, the vacuum, and the body may, let's say, result in some not well positioned body on the vacuum. And so to avoid that there's some misalignment between the body and the vacuum, it is necessary to maintain the body in position through the ejection cylinder. Okay, after moving the arm to the downstream station, you can deactivate the vacuum and also activate the expulsion and then move the arm back to the warehouse. And this complete the process. Okay. Of course, if you have questions, stop me. Otherwise, I move to the testing station, in which we have here, you see, okay, sorry. Let's start from the beginning again. Here you see the lever arm is moved to the downstream station. The object, the body is here, even if the definition of the video is not so good to see it clearly. Here we have the body under the vacuum. So when we activate the motion of the arm, you see the arm moves back, and we have this elevator that moves the body up. There are also here a couple of sensors. One is here and the other is here. These two sensors are used to detect the presence of the piece over the elevator and to detect the color of the piece in the elevator. Actually, you can distinguish through this sensor if the body is black or not. There's no, let's say, really a detection of the color. You can just detect if the color is red or not by checking the output of the signal. But this is important because the black bodies have a different size with respect to the others. And so we need to detect this because this will change the way how we need to manage these components into the assembly station. So this is an important point for the development of this project. You have to read the information about the type of body you have here and take trace of this information through the all the steps, because later in the assembly station, depending on the type of body, you have to perform different assembly operations. In particular, you need to grasp a different piston because the size of the piston changes according to the type of body. Okay, so the elevator can move up the piece, and here you have this plate that is actually a sensor that measure the height of the body. And in case the height is wrong, we have some body that is not and that have not the right height. This component is discarded. If the height is correct, you see there's another pneumatic piston here. This, let's say, silver body here is with the black head. Here is a pneumatic piston that is used to push the body out of the elevator. So if the height is correct, you can activate this when the position is up to let the body move to the next station. Otherwise, you have to move the elevator back and activate this piston when the elevator is down in order to push the body inside this warehouse where you see there are 4 black bodies already stored. This is just an example to show that where the bodies that are not of the right height are stored in this phase. Okay, so you see here the elevator. Okay, let's try to stop it in the right moment. Okay, here you see the body gets in touch with this platform here. Actually, it push a bit the platform if the 8 is correct, and then this is detected as the triggering thing here. Okay, okay, maybe you get it, but it's pretty difficult to see it from this video. When the elevator goes up, the body lift this platform and is enabled to measure the 8 and detect if the 8 is correct. In this case, the 8 is correct, and so the piston here you see is activated and is push the body out to the next station. Okay, this is the testing station. We have the elevator, the color sensor. We have the 8 sensor here. We have, this is a slider with an air cushion that you use to reduce friction, otherwise the object can't slide to the next station. We have another warehouse here for the discarded pieces. We have, okay, other elements. These are all the devices, but I'm not interested in this. I'm more interested in showing you the scheme of this station. So we have 2 sensors, color sensors and presence sensor. We have the elevator, number 4, and the piston. The number 5 is the piston that I used to push the body out. Number 7 is the 8 measurement, and number 3, I don't remember. Okay, so the one is the presence sensor. So this sensor detects that the piece is over the elevator. This is the color sensor, detecting if the piece is black or not. Verification busy is I don't remember this sensor what is used for. This is the sensors used. That's a sensor. Sorry, the activations and the sensor to lift the elevator or to move the elevator down and to detect which is the position of the elevator, up or down. These are the commands and sensor to the ejection cylinder. This is the command to activate the air on the air cushion to let the object to slide. This is the 8 measurement. So I don't get what this verification be. Okay, I got it. I remember now. I don't remember about this sensor because actually this is not needed. I'm sorry. This is not a needed sensor that I suggest you to use. So you can skip this. This is a photocell that detects the fact that the arm has already moved out of the space of motion of the ejection cylinder. You can skip it by using the let's say the 2 sensor detecting which is the position of the lever arm, or eventually you can use it to detect that the arm has already passed out of the motion of the elevator. So it's used to verify that the arm moving the bodies back and forth is not colliding, or the elevator is not colliding with the arm when you activate the elevator. Okay, there's a note on the elevator. The elevator is a double actuation, no retain device. This is important because if you try to use the elevator as a, let's say, conventional double actuation device, you will have trouble because there's a mechanism that disengage the platform from the actuator. Is a magnetic system that is disengaged, and this basically makes the elevator not working, or even worse, if this mechanism is disengaged, basically the platform falls down and also hit the ground quite hard, in a quite hard way, generating a very, let's say, loud noise. So this can be recognized as something faulty very clearly. Say it's not dangerous for the system, but of course it's something that you have to prevent also, because if this happens, you have to recover back by a specific maneuver the actuation. Okay, so this station is meant to measure the pieces, detect if they are correctly in place, detect the color, and lift them to the next station. The initial position, okay, to start, of course, we need an object to be present inside the elevator platform, and we needed the working area to be free, and this is the reason why there was the eventually the sensor that you can use to detect if the arm is in the working region or not. And the initial position is with the platform down and the ejection cylinder retracted. Otherwise, you can't, let's say, receive the body from the previous station. And the air cushion is off while it's not receiving any piece. Otherwise, you will consume the air from the air supply. That, of course, is something that is something that we can avoid. So the sequence is when you receive the piece, first detect that the piece is in place, of course, detect the color, lift the body, measure the height. If the height is correct, you can activate the air cushion and then push the body through the slider, and then move back the cylinder, switch off the air cushion, and move down the elevator. And then this is recover basically the initial configuration of the system. If the 8 check is not correct, you have to move down the elevator and activate the ejection cylinder in order to discard this body, and then move back again the cylinder, and this restore the initial position. Okay. Questions? Okay. I suggest to make the 10 minutes break and then continue with this processing station. Okay, I will start in 10 minutes.
Sorry, Prof. Can I ask you a question? Okay.
Okay, I'm back. Can you hear me?
Yes, Prof, we can hear you.
Okay, so next in our assembly line, we have the so-called processing station. Okay, this is the video showing how it works. So, okay, so just some details here. You see the body is ejected from the elevator by the ejection cylinder from the previous station, slides through the air cushion, and is received by this rotary table that is activated by a motor, in which in this table we have different positions, but just some of them can be taken by the pieces. So you see the piece falls into this position. We have a sensor in this position detecting the presence of the object. The same is in this position and in this position. So we have three sensors. And then the table rotates by 60 degrees to this position, where we have this sensor that is actually a piston that is used to detect if the body is correctly oriented, because it may happen that the body is flipped upside down, and in this case, this cylinder is not able to enter in the hole, and this is detected by the sensors and unable to detect then the correct position of the body. So basically, there's an actuator that you have to activate, and if the actuator reach the final position, then this gives you a feedback, and this means the orientation of the body is correct. Otherwise, it is not. Then it is moved to the here. Okay, you've seen that this going back and forth to detect the orientation of the body. Then the body is moved to the drilling station. Here we have a drill that simulates, is a real drill, but simulates the drilling on the body. Here we have also an old mechanism that is used to hold the body in place. Then the drill goes up and down and is activated to execute the drill. Here you see it goes down, drills, and move back. And then at the sorry, I would like to move back to the video. Okay, here you see the actuator goes up and down. Then here oops, I'm not able to stop the video in the right position. So here the drill is drilling, and then you see the drill goes up, the whole cylinder here is released, and then the piece is moved to the last position where we have this mechanism that is used to push the body to the next station. Here the body is in the last position, and then it is ejected and it moved. The motion is pretty fast, so it's difficult to see in the video, but you see now the body is down here out of the rotary table. So this is the station. In the rotary table, we have an alignment sensor. So also this device is a bit tricky because this rotary table has basically a continuous motion. You can just activate the motor and it just rotates. And you have an alignment sensor that enables you to detect when the, let's say, 60-degree rotation has been achieved. So you have to, let's say, basically conceive this device as something in which every time you activate the motor, you have to detect when the next alignment sensor is detected, and then this means the rotation by 60 degrees has been achieved. Then there are presence sensors. Also, the presence sensors are a bit tricky in the sense that, okay, there's a question, please.
Prof, can we consider some sort of tolerance, or we have to move 60 degrees ad hoc for each movement?
You will realize that there's some tolerance in the sense that you, of course, let's say the mechanism works even if there's some misalignment in terms of some degree. And let's say it depends on how you manage the stop of the rotary table in terms you will realize that it is a bit tricky to fix to stop the rotary table in the right position in the real hardware. You have to tune the mechanism. I give you a suggestion, probably by means of a filter that delay the signal the right amount to hold to fix the rotary table in the right position. Because if you rely on the first activation of the alignment sensor, probably you will stop the rotary table too early to be correctly aligned to receive the piece, or in general to have the piece in the right position. So you have to tune the filter you will apply here in order to achieve the right alignment of the rotary table.
Thank you very much, Prof.
Also, the presence sensors are a bit tricky in the sense that the presence sensors give you, let's say, the right information about the fact that a piece is present or not, only when the rotary table is correctly positioned. Because if there's some misalignment in the rotary table, basically, or you will feel nothing because the sensor is free, there's nothing over the sensor in any case, or because the sensor feels the presence of the rotary table, not the presence of the piece. So these presence sensors can be considered only when the rotary table is correctly aligned. Otherwise, the measurement provided by the sensor is not correct. We have the inspection unit, the drill, the blocking unit, and the expelling lever. Then, okay, the interface to the PLC, electrovalves, and whatever. These are the components if you are interested, but no, not so very interesting. So, classification of devices. Here we have sensors and the rotary table and other mechanisms. So first, the rotary table is a motor basically with giving you the feedback when you have to deactivate it. That is the alignment sensor. So every time you have a new activation of the alignment sensor, this can be considered as the point where the table has to stop. Okay. And this is the feedback from the sensor. This is the alignment sensor. Then you have 3 sensors, 2, 3, and 4, that are the presence sensor in the 3 different positions in the rotary table. You have the command to activate the inspection unit and the sensor giving you the position of the inspection unit. So if this sensor becomes true, it means the inspection unit reached the right position, and then it means the body orientation is correct. This is the drilling unit. Number 7 is double actuation, double feedback. So you can you have 2 actuation signals to move the drill back and forth or up and down, and 2 feedback into the extreme positions. you have a command without feedback to activate the drill, and another command to activate the holding unit. And finally, the last for the expelling lever. So the objective of this section is to verify the orientation of the body is correct, simulate some machining, and move the piece to the next station. So to start the operation, we need the body to be received from the previous station, and the initial position, of course, requires the rotary table to be correctly aligned. So one thing that you have to make, for example, in the initialization, in case the rotary table is not aligned, you have to perform the alignment, of course. Yeah, you will have to basically raise the drill if it is not in the correct position. Of course, everything should be, let's say, off to be ready to receive the pieces. So when you receive a piece, you have to rotate the table by 60 degrees, and then activate the inspection unit to verify if the orientation is correct. If the orientation is correct, you have to move to the next station by rotating again by 60 degrees. And okay, by 60 degrees if the orientation is correct. Otherwise, you can move directly the piece to the last station. But suppose first that the orientation is correct. If the orientation is correct, you have then to clamp the device by the holding unit and then activate the drill. Switch on the drill, move the drill down, move the drill up, and switch off the drill. Okay, this is move back the drill. And then after drilling, you have to release the clamping unit, and then move the rotary table 60 degrees to the final position when the body will be ejected. If the orientation is not correct, you can skip. You have to skip the drill, so you can move directly, even by step of 60 degrees by 60 degrees to the last position, or move directly by 120 degrees to the last position to eject the piece to the next station. And this moves to the last section of the assembly unit. So after the piece is ejected, it reaches a position in which the robot is programmed to get the object independently from the orientation. So we said if the orientation is not correct, we have to discard the object. So if we detected that the orientation is not correct, we have to skip the drill, eject the object, then the object will be taken by the robot and moved to the trash bin that is over here. So in this station, depending on the orientation of the body, but also on the color of the body. And this is important because, for example, the black body is shorter than the others. And so the robot, to grab the black object, has to move to a different position. So to lower a bit down the gripper in order to grasp the object. So depending on the color and depending on the fact that the orientation is correct, it have to move to a different position and move finally the object to a different position, that is, or the trash bin if the orientation is not correct, or the holding unit that is over here, we'll show in the video, to execute assembly. So this video shows the assembly. So here you see the other elements. The robot take the object, put it into the holding unit. The body is hold here, takes the piston, put the piston in place, take the spring, and then the cap over here that is then screwed into the top, and then this is the final object. Okay, you can stop this. So this is the assembly station. Is actually composed by two parts. We have the robot and the supply of the other components, but they work together. So we have the position where the robot, the object, the body is placed from the previous station, where the manipulator takes the object. We have the workpiece holder. In this picture, actually, the parts are slightly different from what we have in the real system, but it's just it's not meaningful for the workflow. And then we have three warehouses, one for the spring, one for the caps, and one from the pistons, and then the final warehouse, the warehouse of the finished products. This is the piston warehouse, and this is the cap warehouse, and this is the warehouse for the finished products. Okay, the input-output interfaces, the components. Okay, we'll skip this. And this is the objects that we have. The classification of devices. The robot is a pretty peculiar thing, of course. It's difficult to classify this as a generic device. Well, I will give you some suggestion to classify it as a generic device. So let's consider the other sensors or the other devices first. We have a sensor detecting the position, the location, the fact that a body is present into the position where the robot is supposed to grasp it. But of course, I said before, the operation of the robot must be driven by the color and the orientation of the object. So then suppose that the object has the right operation. The robot takes the object, move it to the holding unit, that is number 5. Number 5 is a single actuation device with no feedback that hold the body in place during the assembly. Then you have the three warehouses, one for the piston, in which you have double actuation because you have two types of pistons, and depending on which side you activate the piston selector, you will receive one piston or the other. So you have two activation signal to move it left or right, and you have two sensors to detect it is left or right. You have number 2 and number 4 that are the spring and the cover assembly that are basically very similar in the sense they have a single actuation to push a spring or a cover out of the warehouse, and you have feedback from the Isnair piston. So it's a pneumatic piston in which you can detect which of the two position is achieved by the piston. Finally, you have a signal from the cover warehouse providing you information about the warehouse is empty. So this can be used to detect if the assembly can be executed or not. The robot, so let's say this, the working of these devices is clear, but the robot still needs to be clarified how it works. The robot is a bit tricky, but let me say that there are many real cases in which the robot is treated in this way. So the robot has its own program. It means the motion of the robot are predefined. You are not required to program the robot because it's not the topic of this course. And in any case, it's a very old style, boring programming robot. So I I ensure that there's nothing funny into the programming of this robot. So the program that you have just to recall by your controller the program of the robot you need in order to drive the operation, and the robot program is designed in order to provide feedback about what is happening at the robot level. Actually, due to the way how this is implemented, you are not, by the PLC, you are not directly calling robot programs, but the program is always the same. You're just switching the different phases of the robot action depending on the inputs you provide, and you receive feedback from the robot depending on the state of the robot. So basically, you have to think there's a finished state machine controlling the robot, and you can send commands to this finished state machine by means of some inputs from the PLC to the robot. And depending on the state in this finished state machine, you will receive from the robot some feedback through a certain combination of signals from the robot to the PLC. And these are the signals. So basically here you see on the first column the state of the finished state machine driving the robot. Here you have 4 bits that you can use from the PLC to command a change in the state of the robot state machine. And on the last 4 columns are 4 feedback signals that you will receive from the robot once a certain state is achieved. Okay, so you can have different possibilities to control the robot. You can or design a specific finished state machine that is used to send proper command and driven by the feedback of the robot to control the whole operation. That's fine. So you will have a specific controller for the robot that is probably controlled by the controller of the station, that then is controlled by the controller of the whole line, and this is okay. Another approach could be, I don't know if it is simpler or not. From some point of view, I guess it is more flexible, but it's up to you. Again, take this as a suggestion. Since basically you can see all of this line in the robot, then I will comment what these are. As a single operation the robot can perform. This is the reason why previously I said you can recall the robot programs, because you can see each of these operation as a single program that you call, and the robot execute that operation only, even if there's some state machine behind. If you consider this as I said, separated operations, you can consider each of this line as a single device that needs to be activated in a certain sequence depending on the color of the object, the orientation of the object, and then the whole process that you have to perform. So, and of course, by means of some input and output processing, you can adapt these signals and the feedback, so the activation signals and the feedback signals, to a sort of generic device. So you can eventually think to every line in this table as a single generic device that you have to activate in order to control the sequence operation of the robot. It may be more flexible because basically you have not to take care about the fact that you have some activation mechanism, some feedback and so on. You have just to recall from the main station controller what are the sequence of things that you have to do and that's it. But it's up to you. Okay, this is only a suggestion. So what are these functionalities? So basically, you can command the robot to go into the initial position. That is the position where the robot wait to receive the object to grasp and to do something. And in this, when this is achieved, you receive this combination of signals. This on top, you have the names of the signal. The commands from the PLC are just named bit 3210. Actually, you have also another signal that is called bit 4, that is an alarm signal to the robot. In case you activate this signal, the robot is just stopped. Is really the alarm signal to the robot. While these other signals are just names to the feedback provided by the robot. So depending on the color of the object, you can see in case you have to take a black object or a red or silver object. Red and silver have the same size, so you have to command 2 different operations to the robot, and basically receive the same feedback, because the only thing that changes between these two is the 8. The robot will place the gripper in the execution of the task. Here you have the 2 operations in case the object is flipped up down, so black or red silver. So 2 operations again depending on the task and the feedback. While the feedback, because you see the feedback is the same in these 4 cases, because what changed from one to the other is just the fact that you place the gripper in a different 8 and you release the object in a different position, but at the end the robot goes back to the same position. So this is the reason why it gives you always the same feedback. Then you have to take the spring, and this is the command action, and then the feedback. Then you have to take the piston and you get the feedback, take the cover and you get the feedback, and back and take the piston from the assembly station and put back to the put it into the warehouse of the finished products. So this is the type of operation the robot can do. And apart from the fact that, as I said, there's a finished machine behind, and the fact there's a finished machine means that you can't change the order of operation. So you can't put the cover before the spring, for example, or before the piston. This is the reason why we need a finished machine in the robot operation. Otherwise, the risk is to have or to damage something. So there's a finished state machine that received this operation only according to some predefined order. But apart from this, the sequence of operation, the kind of operation that you can command is this, and the order basically is from the initial position, you have to take a black or red silver piece, or eventually if it is upside down, you have to take it and throw it into the trash bin. And after taking it, if it is with the right orientation, the object is moved to the assembly station. Otherwise, it is moved to the trash bin. After moving the piece into the assembly station, if the orientation is correct, you have to take the spring, take the piston, take the cover, and at the end, put it into the warehouse. So the sequence is always the same in this, exactly this one. Okay. So please. Is these 2 lines when there's take black upside downward piece or take red silver upside downward piece. When you command this operation, the robot take the piece and put it into the trash bin and move back to the initial position. Okay, so of course this concludes the operation in the sense that you have not to do the rest. So you have just to call this and back. Okay. Okay. This is the what the robot does, but we have already seen the video. To start, of course, we need the body to be in the initial position. The robot should be in the initial position. The gripper open. The gripper is controlled by the robot program. So when you are in the initial position, the gripper is already open. So no issue. Okay, these are the other elements to initialize the other three warehouses for the cover, spring, and pistons. Everything should be, let's say, in the correct position to be started. And then the sequence is when our workpiece is detected is picked by the robot and it's transported to the assembly station. Then the cap and the spring are moved out from the warehouse. Then if the piece is black, we need to take a silver piston. So we need to move the piston warehouse into the right position to pick the piston with the robot. And if the robot is the spring is available, we take the spring and move to the assembly. Then we take the piston and the cap. And finally, the robot program also include the fixing, so that the cap that is screwed on the body. So the last operation is just the robot takes the object and put it into the warehouse, but is everything inside the robot program. So nothing that you have to take care, but just the activation of the sequence. In case the red or silver body, the only thing that you have to change is to switch the piston warehouse in order to have the right piston in the right position. The sequence is always the same, so I can skip it quite fast. So, evaluation criteria. So what I expect you to do, okay, this project can be implemented in simulation and on the real setup, on the real platform. Of course, to test everything in simulation is strongly suggested for all the reasons that I suppose you have already clear. And what you have to produce as for the other project is a report that could be a presentation or a document to show how you structure your solution and whatever you did, even the results, even if you have videos you want to show, and so on and so on. You have also to provide the code you developed for the whole project. And also, this is true also for the other projects. Before the exam, at least the day before, you have to share with me a OneDrive folder with all this material. So for all the projects, provide me your reports and provide me the code of your project into this folder. I will also show you how to export your projects, in particular in Automation Studio, because otherwise, if you just move the project folder, this usually is a huge folder containing all the compiled objects that are useless for the evaluation of the project. I just need the code. I will show you how to export your code. The evaluation criteria are always the same, but as I said, in this case, there's a strong focus on signal management and also eventually working modalities, inclusions, exclusions, and user interface. So in this project, this part is really important, while in the other, as I said, the focus is more on motion control. So in this case, you have to use generic devices. You have to design the finished machines in the right way, of course, and you have to create a signal generation, signal management, define eventually different working modalities and inclusions, exclusions. Of course, this is something that extend the capabilities of the signal generation as we discussed during the presentation of this topic. So this will be positively evaluated, of course. And the user interface, of course, is also related to the signal management because some of the functionalities of the signal management, of course, needs the user interface. Questions?
Professor, about this project, is it possible to develop it on Automation Studio, or is it going to...
Okay. A good question. Because I forgot to mention this. For this project, because of the hardware platform and also the simulator, you need to use codices. That, let me say, is much simpler than Automation Studio. Much simpler. So I will show you how to use it when we will see the simulations. We have also, because the simulator works in codices, and okay, let me check if I can show it right now for switching to the next. Let's check if it works. Okay, good. Not this. Okay. So, can you see my screen? Yes, I suppose. So this is the simulator of the of this project. It's a simple simulation, but is interesting since it is something that you can eventually also use in a user interface to show what the machine is doing. But in general, this is also used to simulate in this project. This is based on codices. To use codices, we provided into the Virtuale page a virtual machine. There should be already available. I'm checking right now. Yes, there's a Windows XP virtual machine with the codices 2.3 that you can use to simulate this plant. But also the Festo simulator is also available. Okay, this is the Virtuale page. Just show you the page where it is. So, yes, why is not? Okay, this is the Virtuale page, and here you have the material I presented about the first assembly line. Here you have the Festo simulator. So this is the project I was showing in codices. Here you have the groups for this project. These are useful to manage, let's say, the usage of the real hardware, because we have just one platform, and so all the groups that would like to test their system into the real platform will be managed through these groups. Here we have also a quick start guide. I will open it very quickly because there's let's say the procedure to use the real platform, but it requires a bit of, let's say, steps to do everything. And okay, during the next lab session, I will ask the tutor to guide the people that are interested in testing the real platform. If you don't want to use the real platform, you don't need to go through this list of steps. And here there's the virtual machine with codices installed to run the Festo simulator. The reason why we set this virtual machine is because last year we found, students actually found some issue with codices 2.3 and Windows 10, some serious issues. And so we created that virtual machine. So you can use it if you need. It's up to you. Okay, depends if you don't want to install codices or you don't want to try to install codices, or if you need or not to develop this project. Codices is needed only for this project. We will also show you how it works, but it's pretty simple. I will show in the simulation directly. Let me move back to the simulation. So this is codices. Is much simpler than Automation Studio, even if the structure you can recognize of the project from that side is quite similar. There's some difference, but it's similar. So basically you have here the programs. You can, for example, open programs and see the code inside the simulator. This is a structured test program, the same you already learned. The visualization is a bit different because, let's say, codices is more compliant to the standard, and so it shows the variables on top and the code in this middle window. While in Automation Studio, you see, the variables are stored in a separate file. So it's in this sense, every manufacturer have its own implementation of the standard. Let me say that the standard here is much more clear. Then, okay, here you can add your programs and whatever. If you want to see, okay, you can also create data types here. You can create pages for example, to create user interfaces with buttons, virtual panels, with also the states of the machine, whatever. Simulate faults. This is also in simulation. You can simulate faults. There's already what you need in case you want to simulate faults. So this can be also used even if you develop this project in simulation, even during the exam. And here, this is the simulation, so the first interface. This is the hardware configuration, but this, in case of simulation, is not really relevant. Maybe for the people willing to use the real system, we will show you some information. That some of them are also reported in the list of instruction I reported before. I shown you before. Sorry. Okay, so to run the simulation, you need first to log to the PLC. This you see the state of the window changed. This is because now the PLC is running. We are connected to the PLC. Actually, it's a virtual PLC. It's the same mechanism we had in the Automation Studio simulation. And then we can run the code. If we run the code, you see some light turn it on. Then we have to do some operation. I don't remember if I get everything in the right order. And then we need, we need also a panel here. I don't remember which is the right one. This one, okay. To make the machine able to start, we have to press this, press the reset, and then the machine should be able. You see the machine is initializing, even in simulation, aligning the rotary table, put the arms the right way, and now is ready to start. You can put some, I don't know, silver, red body into the warehouse and then start the machine. And you see the process going on. In this simulator, there's already a controller, you can see. This is to show what the simulator enable you to see. All this activation lights and so on are driven by the simulation. Of course, the controller is available here is not what you are asked to generate, because this controller is made in a different way. It doesn't follow all the criteria I presented and so on and so on. So basically, you can use this behavior as a reference behavior, but for example, in this case, there's no management of faults. There's no generic devices. There's nothing we discussed. Okay, so this is a very trivial, let's say, and straightforward way to simulate the process, but enable you to develop basically all the finished state machines, generic devices, and whatever. So my suggestion is first test your controller here, and then when you go to the real hardware, it's just a matter of tuning. Of course, the tuning in the real hardware, I know, can require a lot of time. And this is the reason why first you have to fix the rest. But then is what you need. Question about this?
Yes, Professor. And of course, we are going to make the machine works. For example, if we have a piece in the rotary part and another piece in another part of the machine, so we have to make the machine running in parallel through all of the pieces, or do we have to wait for one piece to get out of the machines and we put another piece?
Let's say it's up to you, but of course, to be flexible is always a good thing. That maybe one a good approach could be let the user to select what he would like to do. So to process one piece at a time, or to put as many pieces as is possible to process along the line. You can also focus on just one of these two approaches. It depends on you, of course. To manage as many pieces as possible can be good. To be flexible can be even better. This is the message. Of course, this will be reflected in the evaluation of the project.
Yeah, of course. Thanks. And another question about the user interface. I see here that we have like everything in the user interface. So do we have to add something? Yeah. Do we have to manage something?
In this case, no, in the sense, okay, it's not required to add. Okay, let me say, it's not required to add something into, for example, the representation of the simulation and so on. But of course, to manage, for example, the signals, suppose that you want to create a specific list of faults to enable different ways of resetting them, or whatever you want to represent as signal management. In this case, you can add what you need. Or maybe you can find a way to implement everything with what is already available. It's up to you, again.
Okay, thank you.
Let me say that these panels that you have here you will see also in the real system. These are, for example, here you have a virtual panel over here. These are, let's say, the virtual version of, okay, this is just to initialize the values. This is what you have in the real system. So you have these buttons, for example, these are the real buttons. These are virtual buttons that has been added and you can use for some reason. Sorry. And the same here. So these are, for example, you can see which is the state of the machine in general. You can use it to drive the system in some way. Okay. So there's not so many time. Please.
I don't get it. This file that is on Virtuale. So inside the there is the simulation and also the logic to simulate everything. But we need also to modify the logic inside to follow the design pattern that you teach to us. Or we need just to manage the signal management about that.
You have to add also not just the signal management, but also to structure the controller in a proper way. Because, as I said, you have to use generic devices. You have to structure the finished machine proper way, create input-output bridges, create the structure of the whole project. So there are different things that you have to make to create a project that is what we said we need. The behavior that you can see here is just a reference. Okay. Okay, if there's no other questions, I would like to present also the other opportunity. Time to show it, otherwise we'll fail time. The second version of the last project, let's say, is more for people working alone, let's say, and it can be developed entirely in Automation Studio. But in this case, you need the industrial physics simulation, otherwise it doesn't work. So this is the multi-box palletizer project. Here you see a video. This is a simulation made in, you see here the Automation Studio part, driving the system. And this is the video showing the simulation in industrial physics. You see the machine, you see the boxes inside the machine, and you see there are devices, there are sensors, I will detail later. This creates a bunch of boxes with different orientations that are then loaded into a pallet following different orientations. Here you see there's this crane moving the boxes over the pallet. Okay, in the video you can see there's sometimes some visual effect that, okay, it's just a simulation, a graphic problem in the simulation is not, say, relevant you will experience more during the simulation. You see also there's some part of the machine that are meant to manage the pallets, to put them in the right position. There are also cardboard that need to be put on the bottom of the boxes. You see here first the cardboard is released, and then you see the cardboard is the dark brown layer under the boxes here that are piled over here. Okay, this shows basically the process. Now I'll go on to show what this is, how this is made. So we have 3 units: the feeder, the crane, and the pallet handler. So the feeder is the first part of the machine. The crane is used to load the boxes on the pallet, and this side of the machine is used to handle the pallets. The objective is to create 2 layers of 14 boxes each, and the layers are formed by 3 lines with 2 different orientations of boxes, and the orientation should be alternated over the layers on the pallet. So this is the first and the second layer. This is the dimension of the boxes. A cardboard needs to be included let's say, on the bottom of each box layers. Okay, I can go fast here. So the first section is the feeder, and these are the devices we have in the feeder. We have the box, but the box is just the box. Then we have the conveyor, the first section of the conveyor. We have a pusher that moves the boxes from that conveyor to the next one. That is conveyor turn 1. These are the name of the devices. This is conveyor if, that is the feeder. It means that puts box inside. This is the conveyor used to turn the boxes if you need to turn them. And this is the last section of the conveyor. So the conveyor is divided in 3 sections. The pusher moves the boxes from that conveyor to this one. You can detect the boxes at the end of this section through a laser sensor here. You have this device that is called turn pusher. If you activate this goes basically close to the middle of this section of the conveyor. So the boxes rotates because of the contact with this element during the motion over the conveyor. And then the boxes moves from this conveyor to the next just because they have the same direction. And there's a sensor detecting the boxes reaches the last section of the conveyor. And finally, there's that carriage that is what is used to move the entire line of boxes to this table that is an intermediate buffer used before moving the whole layer of boxes into the crane. These are the input variables from this section. You have, this is the, let's say, how they are represented inside industrial physics. You have the 2 laser sensors, one at the end of the first section of the conveyor, the second between the second and the third section of the conveyor. You have the position of the carriage, the actual position, and the fact that it reached the target position. Because in this machine, the objective is on the same basically of the previous project. We are not interested in motion control, so basically the motion control is already inside the machine controller. You can just send targets in a simplified way, as there's behind some generic axis controller. Actually, there are. So this is the way how the axis can be controlled. Then there are the pusher feedback, if it is forward or backward position. The same is for the turn pusher. So these are Boolean variables. These are the output variables you can use. This is to activate the conveyor motion, first section, intermediate section, and last section. This is the target position you want the carriage to reach. So you can just give the position and then the carriage will go. And this is the activation signal for the pusher. So it's a single activation signal, single activation device, while this turn pusher is a double activation device that have to signal to move back and forth. Some information about the target position. So this is the target position for the first line of boxes. So, sorry. For the temporary storage. Finally, when you want to load all the boxes on the crane, this is the target position to reach the crane, basically. This is the crane. The crane is composed by two axes, one vertical axis, one horizontal axis. Then on the plate of the crane, we have a pusher that is used to move the boxes out of the crane. It can move up and down and back and forth through these two inputs. X moves back and forth and X moves up and down. And then we have also a couple of rails that can be activated to hold the boxes in position during transportation. Otherwise, during the crane motion, the boxes can move if they are not held by this device. So you need, before moving the crane, you need to activate this to hold the boxes, then move the crane, and then release the boxes to then unload the crane. Under the crane, there are a set of vacuum that are visible here that are used to grasp the cardboard before loading actually the crane and then release the cardboard on the pallet before releasing the boxes. So, okay, back to here. So the sequence is first load from the previous station the boxes on the crane, while this object here needs to be up and backward. So it is, let's say, not colliding with the boxes. Then before moving the crane, you need to activate this rail in order to hold the boxes. Then you can, first you have to move down the crane over the cardboard and activate the vacuum. And then also there's a mechanism to hold the cardboard in place that you need to release the cardboard. Otherwise the cardboard will stay in the pile. And then before moving the crane, to move the crane, you need to set the proper target position to the vertical and the horizontal axis. These are the inputs from the simulation. So the position of the crane and box axis. So these are the vertical and horizontal position of the crane, basically. And the fact that the vacuum is active, so that the cardboard is taken. These are the output from the controller, target position from for the two axes, the cardboard trigger that is used to release the cardboard, otherwise it will remain in the pile. This is to activate the vacuum to grasp the cardboard, and this is to activate the holder of the boxes, and this is to move the pusher back up and down. The pusher is a device that is used to push the boxes out of the crane. So to push the boxes out, you need first to move this down and then to move this forward. So to activate first this and then deactivate them to move back to the initial position before reload the crane with the next layer of boxes. These are the target position for the different axes. The first axis, this is the position of the horizontal axis. So to load the boxes, to place the boxes on the pallet, and this is to place the cardboard. So first you need to move the axis to this position, release the cardboard, move to this position, and then activate the pusher while you move back to the original position, 0, to release the boxes. This is the vertical axis, again 0 to load the boxes, this value to take the cardboard, so you have to lower a bit down the plane to take the cardboard. This is the position for the first layer of boxes and cardboard, and this is the position for the second layer of boxes and cardboard. Finally, the pallet handler. You have 2 sections of the conveyor. You have 2 light barriers here and a lifter and forks to hold and release the pallets. These are the input variables. The pallet lifter axis actual position, so it means in the vertical axis where the forks moving up and down the whole pile of pallets are positioned. This is the feedback that detects when the forks are open, so it means the pile of pallets are released. And these are the 2 light barriers that are used to detect when the pallet reached the last part of the conveyor. Why these are needed? Because after releasing one pallet from the pile here, I will tell you later how to do it, you activate the conveyor, then the pallet moves to the second conveyor, this pallet conveyor 2. Then to stop the pallet in the right position, you need to decrease the velocity when the pallet goes through the first light barrier, pallet light barrier 2, and then stop it completely when it reaches the second light barrier, pallet light barrier 1. Because if you don't decrease the velocity, the problem is that the pallet slides along the conveyor, and so the position of the pallet is not the correct one. Of course, this is to, let's say, be faster in positioning the pallet, but anyway, have the correct position at the end. To release the pallet from the pile, you have first to move the whole pile down, open the forks, move up the fork by the thickness of a pallet, basically, close again the forks and move it again, everything up. This basically releases just the last pallet in the pile, and then you can activate the conveyor to move it out from that region. These are the output variables, the target position for the lifter of the whole pallet pile, the command to open the forks. If you activate it, the forks open, otherwise they close. This is to activate the first section of the conveyor. In this case, the velocity is fixed. For the second conveyor, you have 2 levels of velocity that you can change to this value during approach. So this is the faster motion, and this is the final slower motion to have the final positioning. These are the target position for the lifter of the whole pile. This is the position while you are in the idle configuration, so we are not releasing any pallet. This is the level of the conveyor, so you lift down the pallet to this point to have the pallet in the right position over the conveyor. Then you open the fork, you move up to this position, so basically this is the 8th of the second pallet in the pile. Then you close the second from the bottom. Then you close again the fork and you move everything up to 0 again in order to have just the last pallet over the conveyor ready to be moved. Also in this case, you have to create a user interface also to manage signals, emergency, and whatever information you need to present. So in this case, you have to create the user interface through Automation Studio. How to design it is up to you, and also what kind of things to show are up to you. Of course, the basic ones are start, stop, emergency, and any other condition you want to show. The guidelines are always the same, but in this case, you can use generic devices. You can also use some generic access, even if the, let's say, functionality of the access are very simple. There's already some generic access controller in the background. You can manage the crane, the pallet lifter, and also the pusher in the first part of the machine as something that can be managed as a generic access. A very simple version of a generic access. You don't need PLC open function blocks, to be clear. You need to include eventually some input filtering, because in simulation everything works, but maybe in a real case you have to show that you know how to manage filters. You have to consider fault generation and management, and to manage the different kind of stops, so emergency stop, immediate stop, and on-phase stop. That's it. Sorry, I take this longer than expected. If there are questions.
Prof, I have some question.
Please.
In the first project with 6 people, if I understood correctly, do we have to take the exam all together, or we can take it in separate seat?
It is preferable to have the exam all together.
Okay.
6 people. I don't remember to say
not 6 people. Sorry, I didn't understand.
The maximum is 4 for the second. For the last project. And in any case,
we have to create another group with, or we can just remain with the current one.
You can also remain with the current one. The same, let's say. My suggestion is to maintain the same groups. If at least if you are the point is, if you are a group of 3 people, you can stay the same also for the last project. If you are a group of 2 people or 1 people, of course you can merge 2 groups or 3 groups or more groups to have, let's say, people enough to create these projects that are a bit more complex. But if you are 3, okay, eventually you can join with a people that is alone, with a person that is alone, but maximum 4. Okay.
Perfect. Thank you very much.
And in any case, you can have the exam. It is preferable to have the exam all together, because of course they simplify a lot everything. But you can also have the exam separately.
Thank you very much, Prof.
Other questions?
Professor, about the how to simulate the faults in the second project, in the second type of project, how is it possible to?
In this case, you can through, for example, the input or out bridge, you can create an interface through which you can force some signal to be false or true by just creating, let's say, some button through which you can just fix the value of a signal independently from the output of the controller or the simulation.
Okay, perfect. Thank you very much.
You're welcome. Other questions?
Sorry, can you hear me? No.
Yes. Yes, I hear you.
I didn't understand if the last, the palletizer project can be done just if you are alone in a group, so individually, or in a group of 3, like the other exercises?
It can be done even, let's say, in group of 3. Let me say that is not so complex as a project, for sure not as complex as the first assembly line. So let me say that the evaluation probably is different in case there is a group of 3 people developing the palletizer project, because the load to develop the project is for sure lower.
Okay, thank you.
There's an hand raised, please.
Yes, and how we manage to reach the Festo platform to simulate it? We need to sing somewhere or where it's present?
To simulate the platform or to use the real platform?
To use the real platform, Festo.
To use the real platform during the lab sessions, we will move, let's say, the groups that are interested, of course, one by one, because there's no, or at least maximum 2 groups, to the other lab that is really close, where we have the platform to work on it.
Okay.
Maybe, let's say, this is if you need to work on the Festo platform, on the real platform, even after the end of the lessons, you can contact the tutor, or also we have also a technician that is often present in the lab in order to, let's say, be able to access the platform even out of the lessons. But in any case, I strongly suggest you to first, let's say, check everything, test everything in simulation, because as always, if it doesn't work in simulation, there's no way to make it work in the real platform. Okay, if you have no other questions, just to show you that even for the palletizer project, you have the material you need in the Virtuale page, and that's it. Okay, next time I will also show you how to simulate the palletizer using industrial physics. So today there's no time more. We are already more than 10 minutes late. Sorry, and yeah, see you next week. I hope you stay safe, even in these bad weather conditions. See you. Bye.
Bye, Professor. Thank you.